Hello, welcome to section 13.10, Lagrange multipliers. This is the crowning achievement in our chapter 13. It is a way to find maxima and minima if you have a constraint. So it's going to correspond to finding, for example, maxima and minima on a boundary. It's not about the inside region. For the inside region, we have a system that is pretty good. But if we have just a constraint or a boundary of a closed region, we can use Lagrange multipliers rather than what we have done until now. So let's see that with an example, and we'll start by studying the example and using the system that we would have used until now in AP Calc AB, for example. Find the rectangle with maximum area that can be inscribed in the ellipse given by x squared over 9 plus y squared over 16 equals 1. So the sketch here shows us the situation. We're trying to find the rectangle that has greatest area. If we solve for y, we find that y equals 4 root 1 minus x squared over 9. So we are trying to maximize the function a equals 4xy. Note that maximizing a equals 4xy is the same as maximizing just xy, so that would be an alternative. Since we are focusing on finding x and y, we could ignore the 4 and only think about the area in the end. But we are trying here to maximize a equals 4xy. Substituting y, we get a equals 16x times that square root, and what we would typically do is find the derivative and set it up equal to 0. So that is what happens here. U prime v plus uv prime. We set it equal to 0 and we solve, and the process is pretty smooth. Roots are squared or multiplied with each other, so the root disappears, and we end up with x equals plus or minus 9 root 9 over 2 and y equals root 8, which tells us that the area, the maximum area, is 24. Again, the minimum area would be anything, any point on the axis, then the area would be 0. So that's what we've done until now every time. Let's see the other new way of doing that, which is using Lagrange multipliers. Lagrange was a French mathematician. You've heard his name in AP Calc BC with some kind of error bound. And he's also responsible for the SI system of units. So this is really a wonderful idea that Lagrange had, and it can be related to what you saw in Algebra 2 when you were doing some kind of optimization, when you were given a feasible region and you had to add all the constraints. It's the same idea, except now we have curves instead of lines. So here's how we look at it. It's really clever. Instead of focusing on the ellipse first and trying to find the point that is on the ellipse and that will yield the greatest rectangle, we just look at every point in the xy plane. So here's a point. It's xy. I can draw a rectangle which would have the same behavior as the rectangles in the exercise. It would be a big rectangle like that. And the area of that rectangle would be 4xy. Now there are many, this rectangle is obviously too big, it doesn't fit in the ellipse, but it's interesting because we can think about the function a equals 4xy that gives, for any point, the area of the rectangle. And do you see how this actually defines a hyperbola? As if I choose a equals 40, it's going to define 40 equals 4xy. It's going to define a hyperbola that gives all the points here, 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 where the rectangle has an area of 40. Now again, none of these rectangles fits the ellipse, but we have a level curve where the area is always 40, whatever point we choose. It makes rectangles that are always 40. And there's a level curve a little closer to the ellipse that gives us all the points where the rectangle, if we sketch the rectangle, would have area 30. It's the level curve A equals 30. So 30 equals 4xy. So we have all these level curves, and we are actually looking for the one level curve that suddenly touches the ellipse. This is going to be the point of contact, the point of tangency, is going to be the place that has the greatest area. Of course, the further away it is, the greater the area is going to be. But because we have this constraint of needing to be on the ellipse, we're going to look at the level curves closer and closer until we suddenly touch the ellipse, and we're going to touch it at this point right here, and that's going to be the answer. It's going to be the place that has a point on the ellipse with greatest area for the rectangle. So this is the concept and the consequence. The level curves show points in the plane where the rectangle would have a certain area C, so C equals 40, C equals 30. The level curve with the target value C that touches the ellipse is the best. That's the one we're looking for. At that point, the ellipse and level curves are tangent. You can see it here, it's well drawn, the ellipse and the level curve, which is, by the way, we just calculated it earlier. This is actually C equals 24. We know it from having done the exercise. Normally we wouldn't. But these two are tangent here. What that means is if I take the gradient for the ellipse and for this hyperbola here, for the constraint, these two gradients would be parallel. And if two vectors are parallel, it means that one is a multiple of the other. This sign here is lambda. It's a little more elongated. It's a Greek letter that corresponds to L in English. So, using that, when we want to apply Lagrange multipliers, we are going to always have to write the function that we are trying to optimize, and in this case it's the area. We're trying to optimize f of xy equals 4xy, and we are going to write the constraint. So the function to optimize and the constraint. We could always just write here function constraint. And the constraint is x squared over 9 plus y squared over 16 minus 1 equals 0. It's the equation of the ellipse. So if we take the gradient for both of these, we find del f equals 4y for the first component and 4x for the second component. And then del g is 2x over 9 for the first component and y over 8 for the second component. Remember that these two vectors don't need to be equal, they just need to be parallel. So that's why we multiply by lambda, and here's the vector lambda del g. So we can identify components. We can say that 4y is equal to a certain lambda del 2x over 9, and 4x equals lambda times y over 8. This is going to fix the problem of the gradients being parallel, but we also, of course, need the point to be on the ellipse. That's the extra equation. It's the constraint. We can't just find a point anywhere where this would kind of miraculously happen, that these two are parallel. We need it to happen, but we need it to happen on the ellipse. So we always add the constraint as well in our system of equations. So this is a system of 3 equations in 3 variables. We can simplify here, solve for lambda. Lambda equals 18y over x. Plug in the second equation, and just following the steps by substitution, we can reach a point where we find y equals root 8. From here we find x, and we find area equals 24. No surprise, because we've done the exercise before. But the idea here is so different from what we would do in AP Calc AB, and it's really brilliant. So this is a summary of the Lagrange multipliers. If we happen to have more than one constraint, we will see how we can adapt this. But again, you find the gradient of f, the gradient of g, and then you identify component by component, and you add the constraint itself. So let's see an example here. X squared plus 2y squared minus 2x plus 3 is the function we are trying to optimize, and we have a condition. We are looking at only points that are inside the disk, or inside or on the boundary of the circle x squared plus y squared equals 10. This is what it looks like. This is the graph. It's a little bit jagged, but it's a paraboloid, so there would be normally there wouldn't be any maximum, it would just go up to infinity, but we are only focused on the domain such that x squared plus y squared is less than or equal to 10, so we only look above a circle in the xy plane, and that's why we are going to find a maximum somewhere. The minimum is right there. That's not going to be very hard to find. The maximum is a little bit more complicated because you can see the parabola has been sliced somehow, and the graph is not great. It doesn't show very well. It doesn't show really the boundary very well. So as I said, Lagrange multipliers is used for the boundary. The inside region we saw in a previous section, 13.8, and that's just going to be the best system we will learn. So for the boundary, we have our function to optimize here, and we have a constraint, which is the boundary itself. So the circle, not the inside region. X squared plus y squared equals 10. That's the boundary. The process is very smooth in this question because we're working with polynomial functions. So we have del f equals 2x minus 2 times I plus 4y times j. These are the two components for del f. And then lambda del g. Yeah, we would want for g to write x squared plus y squared minus 10 equals 0. You want to throw everything on one side, and you're only focusing on that function such that it is equal to 0. So lambda del g here, it was done in one step. Del g is 2x I plus 2y j. If you multiply by lambda, you would have lambda pop in here. So we get a system of three equations, again in three variables, by identifying the components. 2x minus 2 equals 2 lambda x, 4y equals 2 lambda y, and x squared plus y squared equals 10. So from here, it's just solving a system of equations. It's not particularly hard. You find a bunch of solutions, and we're going to plug in all of them in the function to see the best one. So on the boundary, it looks like we have 2 points where the z value is 24, the highest points, and then we have a place where the height is 6 approximately, and a place where the height is 16. Let's just look at what this corresponds to. This is the lowest, it's the height is 6. Then we have 2 points here and symmetrically there, where the height is 24, and then the 16 is down there. So with this view, we can see the 16, the 24, and the other 24. With that view, we can also see the 6. For the inside region, we are taking the first partial derivatives and setting them up equal to 0. It's very easy to do in this example, and we find that the height here is 2. That was the vertex of the paraboloid. I'm not going to show it again, but it was the lowest point of all. What you do now, because it's a closed region, is you just simply compare all the answers, and that's how you identify that the absolute max is z equals 24, the absolute min is z equals 2. The last exercise is remarkably complex, and we're going to take it in two steps. Let's read the whole question first. Let T represent the temperature at each point on the sphere x squared plus y squared plus z squared equal 11. Find the extreme temperatures on the curved formed by the intersection of the plane and the sphere. So before solving this entire exercise, we're going to ignore the plane. So the question is just, what is the hottest and coldest temperature on the sphere? So we know the temperature is given by that. We have all the points on the sphere, and we're looking for the highest and lowest temperature. So the max and min of function t. So we can use Lagrange. It's not an inside region. It's like a boundary without the inside, actually. So we can find del t, and we can find del g. G is the constraint, so the constraint is the one that has just an equal sign. It's not a function. Typically, it's given as an equality. It's a requirement that we are on the sphere. So we would change g of x, y, z would be x squared plus y squared plus z squared minus 11 equals 0. So del g yields this, and lambda del g yields that. Now this gives us a series of equations. We can identify components. We will have 3 equations that include lambda, and then we will have the constraint x squared plus y squared plus z squared equals 11 as well. So pay attention to the last equation. Sometimes students miss one here. If we have 2z equals 2 lambda z, one possibility is that lambda equals 1, true. One possibility is that z equals 0. That also works, and these are different solutions. If lambda equals 1, then plug in, going backwards up here, we would find x equals 1, y equals 1, and z equals plus or minus 3 using the constraint, because we have to be on the sphere, so that's how we find the z value. And if we choose z equals 0, then working backward, we would find x and y like that. And lambda, we don't really care about the value of lambda. If we don't need it, we don't have to find it. So it gives us 1 and 2 points here with the plus or minus 3, and then 4 points here with all the combinations of plus and minuses. So on the sphere, there are 6 points that are candidates for being the hottest and the coldest. So what we do is we just plug each of these points in the t function, and we get 33, 33, 29, 20, 20, 10 degrees. So the hottest place on the sphere is 33 degrees, and it happens in 2 points, 1, 1, 3 and 1, 1, negative 3. These 2 points are represented here and there. The coldest place is 10.619 degrees, and it happens at the point negative 11 over 3 square root, negative 11 over 3 square root 0. So it's a point behind over there. So we've solved the first equation, or the first situation where we were ignoring the plane. Now let's add a plane. We are still looking for the extreme temperatures, and we are still looking for the extreme temperatures on the sphere, but not anywhere on the sphere. We also want the point to be on the plane. So think about slashing the sphere with a knife, and where it cuts is this plane here. And so we end up with a certain circle, which is represented in red here. And now the question is, where is the hottest and coldest place on this circle floating in space? So we know it's going to be less than 33, and we know it's going to be more than 10.619, because what we found earlier were the maximum of the entire sphere, and they don't qualify because they are not on the red dashed circle. Likewise, the coldest point is behind the sphere, and it's not on the red circle. So how is that different? Well, it's different because we have 2 constraints. The first constraint is the sphere. The second constraint is the plane. And when you have a situation like that, what you do is you set up del t equals lambda del g plus mu del h, where g and h are the two constraints. So we have a new variable here, and it's called mu, and this is how it's represented. So when we set this up, we can calculate del t, lambda del g, mu del h, and we need 2 equals 2 lambda plus mu. 2 equals 2 lambda y plus mu, and 2z equals 2 lambda z plus mu. So yeah, I think there's a y here missing and there's a y here missing. All the equations are here. We find 3 equations by identifying the components of this equality, and then we have the 2 constraints themselves. So we have 5 variables, x, y, z, lambda, and mu. And if you try to solve this with your TI-Nspire, you will see that it doesn't work. This problem is too hard for a TI-Nspire. So we would use Wolfram Alpha, for example, online. And it tells us that there are 4 solutions, and the temperatures for each of them is 25 degrees, 25 degrees, 30 degrees, 30 degrees. And therefore, the maximum temperature on that floating circle is 30.333 degrees, and the minimum temperature on the circle is 25 degrees. And that's where these temperatures happen. So that's it for the last section in chapter 13. Quite complex, but extremely fascinating idea by Lagrange to solve optimization problems. Thanks for listening.